Morning, everybody. Let's just very quickly just make sure that we understand all the chapters that these things are out of, right? Again, just giving you orientation. The note still applies, right? So these will be right on the question, right? So you'll know which question is which one from the topics list. But if it says second law on it, then it's probably chapter 5 or 6, right? But no friction would be which chapter? 5. Friction is 6, isn't it? Vertical circle 6. Conservation of energy, 8, 7, 8. Like again, those are really close to each other. Technically in your book, I think it's introduced in chapter 8. This could be 7 or 8, both. Springs, so I'd say 8, but also 7. Free body diagrams, it's 5 and 6. Newton's laws, definitely 5. Power would be 7. Vector dot product 7. Work done by a force 7 or something in there, right? Okay, so anyway, just giving you a general idea, right? Which chapters those are from and all that sort of stuff. I'm going to entertain your questions, but first I got some questions via email from people that wanted to remain anonymous. So we'll go over them. Question I got was about this problem right here, okay? And let me very quickly just take a screenshot here and put it, and I'm going to try and make this bigger for you. I have to do a kind of a new system when it comes to reviewing exams, and so I've got to do some futzing around. And let's crop it. Let's see, I just want that part right there. I know you can't see what I'm doing, but it'll make sense here in a second. All right. So the question on this one was having to do with why does the normal force change on this one? Okay, so this is a conceptual question from chapter number 5, I think. And it's a good question because I'm sure that a lot of people just kind of go through and get the correct answers and then are happy, right? But if I draw in the normal force and the gravitational force into this problem, right? I want to take a look at how that normal force gets affected by these other forces in the problem. So, and we're going to do them one at a time. So let's just take a look at force A, right? Now, our coordinate system for this problem really should be tilted. We're kind of used to tilting things, right, as we do these problems. Let's take a look at vector A here. Vector A has components that point this way and also along the same direction as the normal force, right? If I just lay A, it goes down and it points upwards along this tilted coordinate system. So that means that I have a normal force plus whatever A's y component is, right? As well as the mg cosine theta. And I'm just going to assume it's maybe not accelerating or doing anything. It actually doesn't matter, okay? If A weren't there, we would just have this, wouldn't we? We're used to kind of getting that result where this tells us that the normal force is equal to mg cosine theta. What does this new line tell me? Well, it tells me that the normal force is equal to a difference. So is the normal force in this case where I have this extra component of force, is it bigger or smaller? It's smaller than it would be otherwise, right? mg cosine theta is the bottom line. If there were no other forces, it was just normal force and gravity. But when we add this force A, we're taking away from that amount. Conceptually, that A force is trying to lift the block off of the surface. And so if there's an additional lifting force off of the surface, then the normal force is going to go down. Think about it, if you're standing on your bathroom scale and somebody comes in and sort of starts picking you up off of that scale, they don't take you off the scale, they just kind of start lifting you up off the scale, what's the scale going to read, more or less? It's going to read less. Where did your weight go? Well, it didn't go anywhere. Gravity's still pulling on you. But as far as the scale's concerned, some other object is helping to support your weight, right? That's what's going on with this normal force right here. Okay, and can we say the same thing for B? Yeah. Right, B's got components. Yeah, they're slightly different than A's, but they go up the slope, but then also up and away from the slope. And so again, we're going to end up with like a negative By here. Okay, let's look at C and D. What does C do right here? What directions are its components along the purple dotted lines?
Down the y-axis and up the slope.
Yeah, down this way and up this way. And so let's concentrate on this one. This one's acting into the slope, isn't it? So we would get something like n minus cy minus mg cos theta equals 0. And when I solve that, I get mg cosine theta plus cy, right? And so now we see that if you've got components of force that are pushing into the surface, we're going to increase the amount of contact force between them. And then the same thing goes for D, right? What would this be for your bathroom scale example? Instead of the person lifting you up, what would they be doing? Pushing you down, right? Now, again, has your weight changed? No, force of gravity on you hasn't changed. There's just some additional force, right, that's playing around with that contact force between you and the scale. Yeah?
How did you get C then?
How did I, when I was looking at force C? Yeah, here's the, whatever I just did, I have no idea. There we go, okay? So it's this force right here, right? But we break it up into its component parts. Yeah?
Does it matter what order you put B or C in, or A or B?
Oh, for the answer? Yes. I can just tell because of the choices that they gave me. They didn't put any equal signs in there, right? So D is a bigger, has a bigger effect on the normal force. It's more like directly pushing into the surface. C is kind of mostly pushed up the surface. Like if I was really careful, and I probably should have been, like this is a longer component than like that one of C. Whereas for D, I've got to come all the way down here, and then it's got a little short component that way. So D has a bigger vertical component than C does. So that's why either this answer or this answer is the one you have to begin with. But, and then in a like manner, right, those have an order too. The other question, any more questions on this one? Yeah.
When you are solving for the normal force over there, are you dividing by -1 to make those not the right side, like, I guess the right side? So like, how are they coming up positive?
So, like here, I just moved the mg cosine theta over to the other side. The step I never write down that might be confusing you is that I moved it to the other side, so it became mg cosine theta equals n, and then I just reversed it. Because you can write them on either side of the equal sign. So. In physics, we tend to put the thing first that we're looking for, and then its result. So sorry, habit on my part. So the mg goes over, becomes positive. The ay comes over, becomes negative. And then I just reverse the direction I'm writing the equation. Other questions? Okay. The other one I got via email. See, now everybody's going to email me questions before the exam review, right? I think it was in chapter 6. I've been forced to use the Canvas app that I'm not happy about. Has anybody gotten Wiley Plus to open outside of the Canvas app, like in a browser?
Yes, you have to open the book first.
Okay,
Yeah.
that's what my 4B student said as well. It's like there's a cookie doesn't get set correctly, and then it like sits in a loop where it just constantly closes the tab. So okay, all right. I don't remember which one it was. No. Who was a Ferris wheel? There we go. Ferris wheel. Okay. And the question, it was really the same question. I'm not going to copy and paste this one over, but it came down to, well, why is the normal force change? That didn't work. Holy cow. Make a circle. There we go. Why does the normal force change, right, when somebody's riding on a Ferris wheel? And we'll even do a side one just for kicks. At the bottom here, which way does gravity point? Down. At the top, which way does gravity point? Okay, so gravity doesn't, okay. And then on the side, it also points down. We all good there? Okay. So this is a Ferris wheel, right? And on a Ferris wheel, you're sitting. What's your orientation no matter where you are in the circle? Does the thing you're sitting in swing, it rotates, right? So that you're like always, your head's always oriented up and like correct. It's not like a roller coaster, right? Where on a roller coaster, you'd be sitting there and then like that, and then I'm not going to get on my head, right? You know what I'm saying, right? The Ferris wheel, the cart kind of turn. Do we need to go to the Big Fresno Fair? Yeah? Yeah?
Why didn't you make it
Just make it. When I was in college, our college was over the hill from, it used to be called Marriott's Great America. I think it's called Six Flags Great America now or something like that. And they had a whole day that was, basically it was nerd day. The entrance fee to the park was that you had to bring your calculator.
Perfect.
Right? And you just waved your calculator at the entrance gate and they let you in. And it was a day dedicated to like science classes coming, and they had all of the ride engineers there to explain how the rides worked. And they let you bring, normally you can't bring like devices on the roller coasters with you. They let us like attach accelerometers to the roller coaster cars and get all kinds of data and all. It was science day at the amusement park, and we had a lot of fun. We did about 30 minutes of science and about 8 hours of fun. Anyway, normal forces. So which way would the normal force be on a passenger at the bottom? Upwards. Which way would the normal force be on a passenger at the top? Upwards. At the top, they're just sitting normal orientation, right? They're not turned upside down, right? And what about at the side? Also upwards, right? That's kind of what the person is experiencing, right? Okay, so what's the direction of the acceleration at the bottom? Hint, the answer for all three of these is exactly the same. Towards the center. Towards the center in the bottom happens to be up. Towards the center at the top happens to be down. And towards the center at the side happens to be sideways. Okay. At the side, something fishy is going on here, right? There needs to be another force, doesn't there? Acting towards the center. And it's probably like friction or the back of the seat pushing on them or something like that, right? Okay. So there's got to be some additional sideways force. Can't really give it a name other than friction or something. It's not normal. Maybe it's the normal force from the back of their seat or something, but it has to point towards the center. All right, so let's just look at the top and the bottom. since the acceleration is pointed up, when the person's at the bottom, which of those two forces has to be bigger, normal or weight? Which of these two forces has to be bigger? The normal force. Why? The acceleration is up, which means the net force has to be which way? Net force has a direction, same direction as the acceleration. So if the net force is up, that means the normal force has to be bigger than the weight. So that when we add these two together, we get an upwards force that accelerates us towards the center. So which has to be bigger, normal or gravity? Normal. Okay, up here at the top, which way does the net force need to be? Has to be downward. So which of these two vectors is bigger? Gravity, which means the normal force went down. Question?
This is a Ferris wheel, right?
Yeah, it's Ferris wheel. Okay. Now, we did the roller coaster in class, didn't we? Yeah, that worked. Jeez. So, with the roller coaster, right? The orientation is different. Normal weight on the bottom. Here, normal weight going down. Here at the side, normal, not weight that way. Whoops. Weight going like that, right? That's because in a roller coaster, a person, like the plane of contact between the person's rear end and the seat, right? That plane is changing its orientation. Whereas in a Ferris wheel, you're riding like that, right? So that's why the normal force would change. Back to that conceptual question it was asking us, right? Why is normal force different? It's different because the net force is changing its direction. And net force isn't a new force, right? There isn't. So here's a mistake that a lot of students tend to make, and I've noticed you guys have been making it less, which gives me hope for the future. Students will sometimes want to draw a centripetal force. There's no centripetal force, tension, normal force. These are all just labels we give to forces that are already there. Where does the normal force come from? Name the object. The interaction between the person and the seat, right? Okay. Where does the weight mg come from? What object causes it? The earth, the interaction between the rider and the earth, right? Name the object that creates the centripetal force. What is the centripetal force at the bottom? It's the normal force. You could say the net force is pointing that way, but it's the normal force is the one that's pointing towards the center, right? What's the centripetal force at the top? Gravity, right? What's the centripetal force at the top of this one? Well, it happens to be both of them, right? The centripetal force is a force that's already there. It's another name for the force that points towards the center. In other words, you've got to find the tennis ball that's got attached to a string. Okay, so what's keeping the ball going in a circle? Tension. What's the centripetal force? Tension, right? It just happened, right? The tension is the one that is pulling this ball towards the center of that circle. Am I getting it right, Dr. Orphy?
I just heard tension.
That's right. Always got to make sure the engineers agree with us. Okay, so those are a couple of questions I got via the email. What are your questions? Things you need to see right now, homework, whatever.
Number 10 on chapter 8.
10 on chapter 8. Oh boy. Okay. Going to form a line. 8, 10, 7 on chapter 8. Okay. I love this problem. Come on. No. Done. Copy. Put it over here so I can draw on it. Paste.
The part that's giving me trouble is just how to set up the test to see if it makes it through the test.
Right, because they do something mean here where if the block can reach, right, what is its speed? If it can't, right? So like, not only are you being asked to solve for something, you have to set up this test to just even see what it does in the first place, right? So there's a couple ways you can go about this, but like conceptually, what is true about this point right here if the block makes it to that point? It has to be moving, or at the very least have reached 0 right at that point, right? Okay? So if it only makes it to this position, right, then it won't have speed here. Okay? So one of the tests could be, all right, let's find what the speed would be. Let's assume it makes it to B. Let's solve for the speed there, right? Because it was if it reaches point B, what is its speed, right? So we could kind of go straight for that, assume that's the case, see what we get, right? If it can't, what is the greatest height? Okay, so this is the other way to think about it. We could solve for how far does it go in this rough section. What happens if the distance it's able to travel, D, is bigger than L? The length of the patch. Then we know it makes it, right? Okay? But if it's less, then we know it stops somewhere in there. Okay?
When I was doing this equation, you have to have a square root in order to like find velocity. And I see, is that like sort of like built-in safety in a way where if you're getting a number that's not real, then you're going to get an imaginary?
So if we go for the first, personally, I would go for the first, it's just me. I think it's a little bit easier to suss out what's going on with finding a speed right here, but that's because I've done a lot of problems like this. I kind of know what to look for, but it doesn't really matter. But if we do the assumption where, okay, let's find the final velocity right here, okay? That, because it's 1/2 mv squared, and we're solving for a velocity, when you finally solve for that, you're going to end up with a square root of something, right? Well, if it were to stop right here, guess what your square root of something would have inside of it? It would have a negative sign. You'd end up with imaginary numbers, which means you're doing imaginary physics, which means that's not the answer, right? Okay? So that's what Liam's saying. There's a little bit of a built-in safety, right, solving for velocity. So to answer your question, you pick one of those, see if it fails. If it fails, do the other one. If it doesn't fail, then there's two possibilities. You did something wrong. It's always the haunting one, isn't it? Or you've gotten the answer. So the test would be, outside of a green box to type into Wiley Plus, would be to do both of those solutions, see if you get an imaginary number for the one and a real answer for the other. So is that enough for you? Or okay. All right. And then 10, no, I wrote it down, 7. Jeez. That button. Oh, it's a great problem. Don't you hate it when your teachers say stuff like that? All right. What are they asking me to do? A, how far does the block move down the incline from its rest position to its stopping position? So this is like where it starts, and then it's going to come down and it's going to compress this spring, isn't it? So they want that distance right there. I'll call that distance D. So that's what they want for part A. So let's see. I know that work non-conservative, no, that's not how you guys do it. Work other plus energy initial equals energy final. Okay. Is there any work other in this problem? It says it's frictionless, right? So frictionless tells me that I don't need to worry about that. And the only other forces involved in this problem involve springs and gravity. So that means work other is 0. Okay. So I now need to define an initial point and a final point and a 0 for gravitational potential energy. I'll put the 0 for gravitational potential energy right where the box stops, right? The lowest point that the box gets in the problem. So because I drew that line, I know that this angle is also 27 degrees. Okay. Oh, okay, well, we'll get there. So energy initial, what does it have at the initial point? Of gravitational potential energy, right? Okay, where H is this distance right there. All right, and then at the final point, does it have any energy? How fast is it going at the initial point? See, it's not moving. It starts at rest. How fast is it going when it compresses that spring completely? It's also going 0, so there's no kinetic energy, initial, final. So where'd all the energy go? Into the spring, right? At the end, the spring is storing potential energy, which is 1/2 kx squared. Okay. How far does the block move to the stopping point? That can be compressed that far by that. Okay, they're giving me a compression distance and a force. Okay, so do I know M? Do I know the mass of the block? Yeah. Do I know what planet I'm on? Yes. Do I know the height? I can find it. Sort of. Yeah, like I'm looking for D, right? So what's the relationship between DH and that angle right there? D is the hypotenuse. And is H touching or not touching the angle? It's not touching. So it's D sine 27, isn't it? So I know my H. Better write that in. mg d sine theta. Okay. I know my half. Do I know my spring constant? We can get it from Hooke's law, right? So the spring constant is going to be the force needed to compress the spring divided by the distance needed to compress the spring. The force is 280. And the spring, okay. What do we put in for the distance?
4.5 divided by 100.
We need to put it in meters, because we need standard units for the spring constant. So 4.5 centimeters is 0.045 meters. This is in newtons, this is in meters. So whatever that is. What? You found your problem? Was that it? Does anybody else want to see me keep going? Yeah? Okay. 280 over 0.045.
6,222.2. Wait, what?
This the calculator in iPad OS now.
Wait, do another one.
No, I'm done. Bye. It can even do things like okay, now it can't. That worked earlier. I have no idea why it's not working now.
It's reading the dot.
Oh, it's reading the dot. It didn't understand. It's also probably my really messy handwriting. Yeah, we're not going to waste any time on this. The point is, okay, it's getting mixed reviews from my students that have used it, right? It tends to not, like it can't do some crazy stuff. Like I don't think it does. Yeah, it just kind of.
Because you haven't updated to the AI version yet.
Is that what it is? Yeah,
I'm pretty sure it's locked behind.
yeah, it's probably, yeah. So anyway, 6,222. My question is, when is GoodNotes going to get that? Newtons per meter. Okay, so there's my spring constant. So we know K. Ah! Okay. And then X.
It's given in centimeters.
Oh, it compresses by 4 centimeters. Oh, okay, then I know X. I was worried there for a second. Okay. So what's the only thing I don't know in this entire statement right here? That's the only number I don't know, right? Solve for D. So I'm going to divide by mg sine theta on both sides. So a lot of stuff cancels on that side, and I get D. And over here I get a K and an X squared all over an M, a 2 and an M and a G and a sine theta. So that's 6,200, I'll do it over here. 6,222 all over 2 times 14 times 9.8 times the sine of 27 times a 0.04 squared. Why did I put in 0.04? Got to convert it into meters. Did anybody have that yet?
I got 0.079 meters.
0.079, so 0.08? 0.079 meters. Give me a second. Meters. Before I hit the magic button, ask your question again.
Wouldn't our sine data be negative in this case?
No.
Because that's our positive.
This is energy. It doesn't care about direction. All right. Submit. So annoying, isn't it? So annoying to see somebody do it the first time correct once, right? The thing is I had 37 of you helping me. You make me look good.
I'm trying to call we reached the high points.
All right, what is the speed of the block just as it touches the spring? All right. So now we alter things just slightly, don't we? Where's our final point going to be now? Why does it keep doing that? The final point is going to be right as it touches the spring. Okay? So again, I'm going to kind of alter where my 0 is. Altering my 0, does it change the relationship between the vertical height and the distance it travels? No, it's still d sine theta. None of that changed. The same triangle. I mean, this is still 27 degrees, and it's still not touching the angle and all that kind of stuff. Do you agree that this is d sine theta? Okay. Now, I draw a smaller triangle with the same angle. These numbers are different now. But is this one still d sine theta? Is the relationship still the same? Yes. The numbers are different, but the relationship is the same. Trig being trig and triangles being triangles. What do they call those? Similar triangles? Identical triangles, but different in size? I don't know. I don't care. Okay, so now that we got that, is our initial energy still mgh? Is our final energy still 1/2 kx squared? No, right? Because we're right before we start compressing the spring. So what energy does it have at the final point? It's got kinetic. I changed my 0. I can do that? Yeah. So I changed my 0. Let's see what happens. mgd sine theta equals 1. What am I solving for? What did they ask for? What is the speed of the block? Okay. Do I know m? Do I know what planet I'm on? Do I know d? Yeah, it says that it slides. Where was it? Oh, it didn't tell me what d is, but I can find d. Because d is going to be equal to whatever the whole distance I got last time. What was it? 0.079 minus 0.04, wasn't it? Yeah, that's my d. That's I'm just going to call it 0.04 because I won't want to keep doing math. Okay, so there's my d. I know the sine of my angle. I know my half. Know my m. Solve for v. Okay, mass doesn't matter apparently. 2gd sine theta, getting rid of the half, and square rooting everything. So v is equal to the square root of 2 times 9.8 times 0.04 times the sine of 27.
1.86.
Thank you. 1.86 meters per second.
Is it because you rounded up to, and
It could be.
it's not liking it?
You point 0.039, yeah?
I didn't change my 0, so I kept the potential energy. And that's
Oh.
I was in radians. I got 0.589.
You were in radians?
Yeah, I was in radians.
You're a math student, aren't you?
I am a math student.
What was it? Point
0.589.
0.60? Is that what I'm hearing?
Never trust you again, Liam.
No, we'd all do good if we followed Liam. Yeah, so that was just a calculator mistake. But the reason I didn't have, you didn't change your 0, so you probably had to include in there that extra distance anyway. It'd make it.
I did like our total height.
Yeah, same difference. Yeah. I just chose to change my 0 because I have that power.
Yeah, it's probably easier to do that right.
That's why, yeah. Lewis. You can't alter the 0 for a spring. The spring's 0 is always at its resting point.
So you're changing the 0 for the block's position, not for the spring.
I change 0 for gravitational potential energy, right? The mgh, and where I measure h from, we're free to pick that 0 wherever we want. Doesn't have to be. Well, and for the blue problem, it is the lowest point in the problem, right? It got to that point, and I just said, okay, well, that's my new low point. So. Does this kind of stuff help, or does it just like make you more anxious?
A little bit of both.
A little bit of both? Where's the anxiety coming from?
Not knowing what's on
Yeah, there's no way I can do this. Okay, number one, that's not true. Number two, you're feeling like you don't understand anything, and that's not true either. You understand more than you realize. It's just that you feel like you can't do it perfectly. And I don't expect you to do it perfectly. I expect you to make a minimum of 2 errors to get an a minimum of 6 mistakes to get a C, right? It's not about perfection. It's about what you know in your head, right? So your goal tomorrow isn't to get a specific score. Your goal tomorrow is to show me what you know, right? Try to get as much down on the page as you can to show me what's in your head, what you've learned. Let me make the decision over whether or not you got the problem right. And whatever you do, do not compare yourself to me, right? This is my job. I'm supposed to come in here and make it look easy. It's not easy. It just isn't. But normal, everyday people pass this class, do just fine, go on and have wonderful careers, all that kind of stuff. It's totally doable.
In what scenario is the normal force in a vertical circle 0?
The normal force would go to 0 for a vertical circle if you hit a tangential speed that is a very specific number. And we found this number in class. Give me a page. There we go. It has to happen, I think. I guess it could happen regardless of what side of the hill you're on. Yes. So let's take the case of like a car going over a circular hill, right? So like the car, right, is driving along a road that's got a circular hill in it, right? And we're looking at the car right at the top of the thing. So it's going to have a normal force pointing up, a weight pointing down. We know the centripetal force has to be down. And so if we write out Newton's second law for that one, making down positive, because that's the direction the acceleration is pointed, that's going to be mg minus n. So now I solve, right? And I move n over to the other side. I move my ma over. And because it's a circle, the centripetal acceleration is equal to v squared over r. All right. mg minus v squared mv squared over r. So the question becomes, right? What is the normal force, right? What is the condition where the normal force would be equal to 0? Right? So can n equal 0? That's the question I'm asking. Well, let's find out, right? Is there a situation, so I move mv squared over r equals mg, and sure enough, there is a non-zero speed that, and it's also not imaginary because it's got a radius and I know what planet I'm on. So what if the car achieves that speed, it will no longer, there will be no normal force between the surface, between the car and the road. If it goes faster than that, it's coming off the hill because gravity can't keep it in the circle that it's going. For a roller coaster where it's inverted, okay, I think we get the same result.
So if I got a negative number for my normal force, I know this thing's starting to fly off and take spread wings.
Right. Yeah, it would just be weird. Because, yeah, negative, well, what does that mean? Right? Did I answer your question?
Yeah.
Okay.
On number 9 on chapter 8, could you tell me why we don't have work other?
Number 9. We do have work other.
I tried solving for it, and I got it wrong, but when I removed the normal force to solve for distance,
That doesn't sound right. Does anybody know a better way of doing what I'm trying to do here?
I do screenshots.
Well, I just did screenshot.
Oh.
I copied it to the clipboard as opposed to putting it in my photo library. Does anybody have a better workflow for getting like homework questions out and into your note-taking app? Because I haven't found one that's faster than that. There's multiple ways to do it, but like that one can do faster. Okay. There is work other here, right? So work other plus energy initial equals energy final. There is work other because we have friction. It's going to be minus F times D. Okay, where's my initial point? Put it here. And where's my final point, right? What do they want us to find? How far does it go? Yeah, stops it in a distance D. So here's my final point. And my 0 for gravitational potential energy will be right there, because that's where they're referencing their H from. Great. All right. So an energy initial, what kind does it have? Is it moving there? Yeah. 1/2 mv naught squared. Is it have gravitational potential energy? No. It's at 0. Here's my 0 line. Right? Yeah, now is it going to go down? Does it have potential energy with respect to this point? Yes, all that's true, right? But whatever potential energy it loses turns into kinetic energy, which then turns back into potential energy, and we're right back to where we started. Okay? So with the 0 right here, again, I'm kind of breaking a rule. I didn't put 0 at my lowest point in my problem, right? Caveat, I don't know how deep this is. Right? So I'm not going to reference that point. I'm going to reference that one, because that's where they told me an H. All right. So it's just got kinetic energy at that point. All right. At the final point, is it moving? No. Does it have gravitational potential energy? Yes. And is there any spring there? No. So that's all I got. Let's hope it's enough. What's friction equal to?
I made an algebra error, but I think I just lucked into the right answer.
Lucked into, yeah, because it sounded like when you say I took the normal force out, I'm like, algebra error somewhere. Keep going. A lot of people won't see it. Now I know who hasn't finished the homework. Okay, so that's what friction is, and I worked really hard to not do the pun. What's the normal force? I didn't say it. What's the normal force? mg cosine theta, but the theta here is 0 degrees, isn't it? So just mg. All right, so minus mu mgd plus 1/2 mv naught squared equals mg. All right, so what do I know? Do I know mu? Yes. Do I know the mass? Yes. Don't need to know the mass, actually. Do I know what planet I'm on? Do I know D? No. But that's what we're looking for, right? So it's okay that we don't know it. We know M. Do we know V naught? Yeah. And then we've covered every. Do we know H? H, 0.92. Yeah. The only thing I don't know in that statement is D, isn't it? All right. So algebra. It's going to be negative mu mgd equals mgh minus 1/2 mv naught. Can I get rid of the m's? There's an m in every term, right? In other words, if I divide every term by m, they just cancel each other out. Okay, so I'm gonna divide everything by a minus sign to get rid of those minus signs. What am I left with? That's mu times g times d equals negative gh plus v naught squared over 2. I just moved the 1/2 down there for some reason. I don't know why. All right, so let's see here. Divide both sides by mu times g. D is equal to v naught squared over 2 mu g minus h over mu. No, I won't do the numbers, but that's what it is. So. Questions, comments, concerns? Where are we running into trouble in these problems? Setup? Algebra? All of the above? Yes.
There can be multiple ways to get to the answer, right?
Yeah, because there's multiple places you could pick zeros.
I use the word friction and network equations.
That's what this is. This equation is what you just said, encapsulated in the ideas where the work done by gravity is mgh, the work done by friction, right, is work other.
So like the one where it's like I ended up using the where it's work and that equals delta K.
Yeah, because the change in kinetic energy, I've shown this already in class, is sitting right there. When you move energy initial over, work other equals a change in energy. Change in kinetic energy, change in gravitational potential energy. It's all there. This is why I don't like chapter 7. I don't understand why they call all that stuff out, because this solves them all. One equation to rule them in the land of Mordor where the shadows are. Rings of Power, by the way, season 2, big thumbs up. Yes. Season 1 was great. Season 2 was better. That wasn't a question about Lord of the Rings, so. No, what is it? Number what? Oh, wait. Oh, chapter 7.
Chapter 8 in question 7. In the speed, you have square root of 2g sine everyone. Or like the
Was this 7?
No, back. It was the longest one. That one.
This was 7.
Okay, so D is the first spring, distance and the distance from
Yeah, so we found this distance as 0.08, right? And then we subtracted out the 0.04 that the spring compressed, because our first answer included the 0.04. And I just wanted to know how far this distance was. You're welcome. Yeah.
Did you go over question 12 on chapter
6? Did you say 12? This one? Hated this problem? That's not relevant. There we go. Okay. It's going in a circle, so like what do we know? What are we up against? It's centripetal acceleration, circular motion. There's certain like equations that sort of are part of that. There's one of them, right? But we're going to do Newton's second law because it comes out of that chapter, right? So what do we got going here? We need a free body diagram of these masses. So the little m, I'm going to draw this. How do you draw this, right? Like little m, if I drew like that picture, it's like a side view, isn't it? Like where it's sitting on the top of the table, right? But there's this tension that's pulling it inwards, right? As it goes around in a circle. There's a tension that exists right there in 3D space. There would be a normal force, and then there'd be a gravity going into the table like that. But do the normal force and the gravity alter this circle at all? No, they're pointing in a direction that has nothing to do with this circle, right? So whereas I could draw the y direction for this one, I'm not going to. I'm just going to worry about the x direction. It's really, this x direction right here is the only one that's causing the circular motion. The centripetal acceleration's that way as it goes around in this circle. All right, so if that's the case, then what does my equation look like? It looks like mass times centripetal acceleration, and then the only one I have is the tension, right? Call it positive, pointing in that direction? Sure, why not? Okay, all right. So there's that. Now, what about the free body diagram for the hanging mass? Big M. I'm going to call this one M1 and this one M2 because my big M's and my little m's look the same. Okay, so what's the acceleration of the big M? It's at rest, which implies it's not changing its motion, so its acceleration is 0. And then it doesn't really matter which way I call positive or negative because there's no acceleration here, so why not up? T minus m2g. So what's the tension equal to? So where's that go?
Go back in the first one. And now we solve for B.
Insert my centripetal acceleration, right? And away we go. Can't cancel those masses because they are different. So this is the square root of m2 over m1 rg, isn't it? And apparently that comes out to that number. I really want to waste your time right now, but I'm not going to. I was going to try to make the calculator work again. Yeah, Edward.
Question for the first one. A for question 5 on chapter 8.
Chapter 8. So you're asking about part A, right?
Yes.
And your question is, why is it the same?
Yeah.
So what kind of energy does it have at this first hill? It's got potential and kinetic, right? And then it goes down, losing some of that potential energy to kinetic energy, and then it comes back up to exactly the same height. So it gains speed and then loses speed coming back up, but it comes up to exactly the same height. So what's the speed going to be? The same as what is it, like conservation of energy, the same as it was at A. Now, why is it going to be different at B? It's got a different height, right? That height has been turned into additional speed. So, did I answer your question? Yeah.
Go over question 6 in chapter 8. I got stuck halfway through.
You got stuck on what?
I got stuck halfway through, so I got to C, and then I tried setting up the equation where like work, there was no work other, and then it said potential energy is 0, and then final 0.
Let's do, can I? No, that's not going to work. Which part was it again? C. So the change in gravitational potential energy when the stone moves to release point. In part A, in part B, because in part A you find the spring constant, which is that. And then for part B, you end up, you find out what the elastic potential energy of the spring is, right? Like how much it's stored. So for part C, right, you've got this stone, it's stored energy, it's done whatever it's going to do, right? It's compressed itself a distance x. And now they're asking, right, what is the potential energy of the stone above this release point? Right? What's the potential energy of this point? Well, where's the stone going to get its energy from? Where does the gravitational potential energy come from? The spring, right? The spring pushes on it, right? Pushes up, it gets to max height. So it started at 0 speed, it ends at 0 speed, but it started with, 100 joules of potential energy in the spring. How many joules of potential energy are now going to be stored in gravity? Conservation of energy, it's 100 joules, right? So that's why the answers to B and C are the same. Whatever this number turns out to be is the answer here, because what they did is they, in a very complicated way, asked you, where does the energy in the spring go? It goes into gravitational potential energy. Is it not taking your answer for the same? It did, yeah. So it's the same thing. So if you want to do a mathematical version of that, there is no work other in this section. There's no friction. There's no air friction. There's nothing else acting on the stone. So whatever energy we begin with is the energy we end with. We start with this, which we already found out. We're looking for this, but we're not looking for M. We're not looking for G. We're not looking for H. We're looking for that whole thing, right? So if this is 100, then what is this whole thing? It's 100. That's what the equal sign means. So yeah. Apparently the question wasn't hard enough, so they had to ask it weirdly. These are the kind of things I try to catch and change on exams. Can we just do all of the homework?
That's the only one I couldn't finish.
The skier?
Yeah. I don't know why. Everything's wrong.
Everything's wrong. The universe is conspiring against you. You got that? Okay, good. Yes! Got to take those small victories. Got to take those small victories. Okay. Ski jump. So we've got a skier going off of a ski jump. Whee! Skis. And ski ground 16 lens from the lawn. Oh, I cut it off. How much is mechanical energy reduced because of air? Oh, okay, so again, they're asking it weirdly. They want work other. Okay, so We're solving for this. Don't break it down. Don't make it FD. Just it's work. It's work. It's work. What is it? What energy does the skier start with? If I make that 0 and I make this my initial and I make this my final, it starts with kinetic, 1/2 mv initial squared plus mgh. And then what does it end with? Kinetic. But I say 0, right? They gave me this 13 meters from where it starts to how low it goes. So we'll put 0 where it ends. And so now, right? I solve for this. V final squared minus V initial squared minus mgh. That should be it. I heard that. Do you want me to go and do the numbers here, or should we move on? Okay. Question 12. We did that one. We kind of did that one. This one is like the last two combined. You got to do a test, right, to see whether or not it's going to be there. But then once you've figured out what your test is, this. Okay, 12. Okay, coefficient, how fast is the crate moving? How far will it slide? Do the answers, okay, all right. Zoomies. This is the mark of technological progress. I used to be able to do that action in 2 taps. But now that we've upgraded, it takes about 7. All right. Top of a ramp. We know the length of the ramp is 4.7 meters. We know the angle is 39. We know friction on the ramp. Oh, interesting. Oh, and the floor is the same. I thought they were going to make them different. That would have been fun. No fun. Okay, so part A, how fast is it going? So my initial point is with it right there. My final point will be when it gets to the bottom. And I'll set 0 to be down there at the floor. So is there work other? Yep. Is there energy initial? Got potential energy, but not moving, right? Starts at rest. And then at the bottom, what kind of energies does it have? Does it have potential at the bottom? No. Does it have kinetic at the bottom? Yes. Okay. How fast is it going? Okay, so we're solving for V, but we got to find work other. Friction is involved. It's negative F times D. This is going to be mu times N times D. And what's the normal force going to be in this case? mg cosine theta minus mu mg cos theta times D plus mgh equals 1/2 mv squared. Got to solve that for V. But before I do, what can I divide every number by? My palm rejection isn't working. Okay, so that gets rid of all the m's, right? So that means that 1/2, just reversing 1/2 v squared is equal to gh minus mu g cosine theta times d. Multiply by 2, take a square root. We got the velocity. Okay. How far does it slide against the floor, across the floor? Okay, so now we got a different problem, right? We've got an initial point here. We've got a final point here. A 0 for gravitational potential energy. When we set that one up, we do have work other. What's our initial energy? And then what do we have at the end? 0 gravitational potential energy and 0 kinetic energy. The V initial I've written in blue. Where does it come from?
Comes from part A.
Yeah, it's the V final from part A. Whatever part A's final velocity is right here becomes the initial velocity for part B. Sure. Yeah, you'd end up with 2 work other terms. You'd have to do the work on the slope and the work on the floor. We've already done it, so I'm not sure I want to do it again. This gets to Lewis's point. There's multiple ways to do these. This isn't necessarily the best way. It's just the way I'm doing it. My way is not the best way. On the floor, this is negative FD, which is negative mu times N. And on the flat floor, what's the normal force going to be? Just mg, cosine 0. Solve for D. Yeah, you can get rid of mass, right? So do the answers A and B increase, decrease, or remain the same? Same, because the mass canceled out. The answers to A and B are different. But part C says, do the answers to A and B change if the mass changes? And the answer is no. It feels like magic, but it's actually science. All right. What are you going to remember by tomorrow morning?
Everything.
No. The wrong answer.
The world.
No. That you deserve to be here. You're in the right place at the right time. You've done the work, whatever amount of work that is, and now it's just time to find out what's in your brain.